Good morning, everyone, and welcome to this morning's seminar on geotechnical stability of final voids as non-use management areas, hosted by the Office of the Queensland Mine Rehabilitation Commissioner. It's great to have so many of you calling in from across Queensland and further afield. To start, I would like to acknowledge the traditional owners of the lands across which we're meeting today and pay my respect to the elders past and present. I also have a couple of housekeeping items to cover before I hand over to today's MC. Today's session is being recorded and will be made available on the OQMRC website in the coming days. So if you do have any colleagues who couldn't make it along today, please feel free to share a link to that recording. During today's session, we're going to have plenty of time to ask the presenters questions. So please use the Q&A function in the top of your toolbar to send through questions throughout today's session. They may disappear from your screen. However, our team will receive all of those and we'll get to as many as we can. With that now out of the way, it's my pleasure to hand to today's MC, our lead technical advisor, Louisa Nicholson. Over to you, Louisa.
Thanks, Sam, and welcome everyone. It's my pleasure to be MC for this event this morning. And part of the role here at the Office of the Queensland Mine Rehabilitation Commissioner is to engage with our stakeholders and community, and we raise awareness about mine rehab matters, as well as producing the technical reports on leading practice rehab of land. And that's why we're here today. It's obviously you're aware that we published a practice note late last year, and the purpose of that practice note was essentially to summarise the components of a leading practice assessment regarding of long-term geotechnical stability, particularly of voids, that was published in a very detailed study, part of an ACARP project by John Simmons and also Greg and Sue, who are with us today. And so the role of the practice note was also to promote a consistent understanding of what's required for our mine operators, regulators and technical reviewers when it comes to these geotechnical assessments, as well as clarifying the required assessment components and the role of professional judgment in this assessment and the limitations of prediction, which is quite important. This a process that is talked about in the practice note is a certifiable process accepted by industry and regulators. And so we're very excited to have been able to bring this work to you. There are a few definitions that will be handy as we start to get into the weeds this morning. And so I just wanted to cover those quickly before I introduce our speakers to you. Firstly, what is a final or a residual void? Well, in the context of this work, we're talking about excavations that were made in order to carry out the mining activity and that have not been backfilled to at least the post-mining ground level, and so they remain in the landscape. And in Queensland, we have NUMAs, for those who aren't aware. A NUMA is a non-use management area and is defined in the legislation as an area that cannot be rehabilitated to a stable condition. And stable condition is also defined in our legislation, and it means the land is safe and structurally stable, that there's no harm being caused by anything on or in the land, and that the land can sustain a post-mine land use. And so when the residual voids that we have after mining can't sustain a post-mine land use in Queensland, they likely meet the definition of a non-use management area or a NUMA. Now, NUMAs are approved under particular conditions, but that doesn't mean they don't require some sort of rehabilitation activity associated with them. And a NUMA must achieve best practice management and minimise environmental risk, which is another reason why this work is so important, because geotechnical stability is a key element of NUMA management. And so with those definitions out and we are aware of what we're all talking about together and we're on the same page, it's my pleasure now to introduce our authors for this practice note who are going to present to us today. So it's wonderful to have Greg join us. Greg is a principal engineering geologist at PSM. He has over 16 years experience working on various domestic and international mining and civil engineering projects. Greg's worked on projects across Australia, Asia and the Pacific, and interestingly, this includes covering as the geotechnical superintendent role at Oktedi mine in Papua New Guinea. I suspect, Greg, that was quite interesting but challenging all at the same time. Greg's an accredited RPEQ in civil and mining in Queensland and a slope risk assessor under the New South Wales RMS RTA slope risk assessment program, which is great because that means we've got some good practical local knowledge here in the team. Dr. Sue Henderson is a civil and geotechnical engineer at Hendo Geotech, and Sue has more than 35 years experience in consulting and research. Many of us know Sue, and she's been a large figure in the industry for quite a while. Sue's been mainly involved in surface geomechanics, and has been a key researcher on several ACAR projects and has also served on subcommittees negotiating with the government on dam conditions, water conditions, rehabilitation and closure. So without any further ado, welcome Greg and Sue, and I'm looking forward to the presentation. Thank you.
Thanks, Lisa.
Okay, thank you everyone for turning up. Into the process itself, we've got some more concepts or definitions to set the stage for geotech stability. So if we can move to the first. The difference between geotechnical and erosion stability sometimes gets. Geotech is the lack of excessive ground movement caused by loads or stresses within the ground. Erosional stability, by contrast, is the lack of excessive loss of ground material caused by water, usually out at the surface, but definitely at the interface with those. So we've got the example that you probably all recognise as geotech instability. Something down near the toe of that wall obviously wasn't quite strong enough to hold up. So you have the material falling out quite a large amount and that scarp shape. Erosional stability, also very familiar but quite different in shape. This one, no argument that it's big and ugly, but it's a completely different mechanism. They need complete sets and professional training to assess. They can interact, but they're not the same. You can imagine cases where a scarp like that geotechnical instability could lead to greater erosion. There are also limited situations, but they do occur, where you can trigger geotech instability. For example, if it's at an angle and undercuts a bed or something like that. So in long-term geotech stability assessment, one must consider the potential for erosion to impact, but it's not the same thing. So geotechnical assessment is not an assessment. Next one that we need to hammer home, and we will be for some time in this talk, is that geotech stability is not a certain thing. We can't quote it to 3 decimal places, or if we do, we're kidding ourselves. Some of the reasons the profile has not been designed by us. Whoever put it there is a bit wacko at times. So there's random layers and pockets. Soil and rocks are not manufactured materials, so they don't have a predictable QA'd band of properties. The properties they do have can vary with the geomorphology, also moisture content, time, and of course spatial variation. The models that we use to analyse stability are approximations, and how accurate a particular model is really depends on how well it captures the important aspects in this particular situation. So the upshot of that is there is no single correct answer for stability. Instead, what we as geotechnical engineers have to do is define a threshold or an acceptable outcome that's based on both the confidence we have in our particular model and method of analysis, consequences of instability. And that requires judgment. It's not something you can dial up out of a recipe. So that's where the professional training and experience comes in. Given the uncertainties, the load history, moisture effects and things like that, an appropriately qualified person can't guarantee stability for a significant time into the future. All we can certify is that we have evaluated stability using sound and accepted procedures. Next idea here to put out is that it's not about maximum or minimising risk of instability, because what you do to improve stability can make other aspects of your NUMA worse. First example, flatter slope usually improves stability, and it certainly can reduce uncertainty. However, it also increases your void footprint. It may increase the catchment, which leads to a high pit lake level, which in turn might saturate more of your low wall and change your stability. The longer slope may actually be subject to increased erosion, and flattening the slopes, particularly where you've got a dump, will reduce your dump space that way, so that what you would have put there, if you could have justified a steeper slope, you've got to find somewhere else to put that material. Another example, partial backfill of voids, that can improve stability, usually by just reducing the exposed height of your walls, but it can lead to pit lake, and that might turn what would have been a void that is a sink for groundwater into a source of contamination to aquifers. So once again, we come back to this, rather than maximising stability, aiming for an acceptable level of stability. That depends on consequences, and considering that, particularly in the context of this practice note, we've got a NUMA, but it's got usually adjoining post-mining land use areas. So while this practice note is about the NUMA, one does have to give consideration to the adjacent land. So if all of these things and bad news about what we can and can't do hasn't come home, the basis is we can't certify in the long term. If we're uncertain now, the uncertainty can only multiply the further into the future we go. Trying to, in the ACUP, assess what's a reasonable frame. If you think about living memory, 60 to 80 years. There are photographic records of landforms in Queensland in our area of about 160 years that you could use to gain some insight in the long-term changes. In civil fault design life is about 60 years. Even your critical infrastructure like hospitals is only about 100. So they set the time frames on which accepted understanding is that we could reasonably make some forecasts. So on that basis, we're suggesting that the range for long term is in the order of 60 to 100 years, to be decided at each assessment based on the information you have, the complexity of your model, how confident you are. Quick pause for any comments or questions on that stuff.
We haven't any questions across into the chat or the question and answer yet, Sue, so we might just keep going, I think. Thank you.
Oh. Okay, now we're on to the elements of the assessment process that are in the practice note. In the rest of this presentation, we'll go through these in detail and with examples. The point of formalising this is to provide confidence in the process, but still allow this professional judgment that is the core of geotech engineering. What I want to stress here is that none of these elements are new to the geotech engineering or stability assessment. Any competent geotech will be doing all of these in their assessment already. The difference here is that we've set out a framework that you can formally document them, and in a couple of places provided a way to compare and report uniformly across different assessments. So the first component, statement of design intent, is really where the geeky engineer just communicates out in the report to the audience what the point of it is. It's a typical scope and limitations type introduction to a report. Obviously, the purpose, the location of the NUMA, given the number of PRC peer revisions I've done, that becomes very important. The time period that you have assessed that, where in the 50, 60, 200 years you feel confident to forecast, and importantly, any changes that would mean you need a reassessment. I'm not going to go through this. It's just an example of a statement that I put in, so it'll be in the slide pack and presentation, but it's not a difficult thing to cover, just important to put it there to hold the whole assessment together. Now we get on to some of your engineering stuff, and I'm going to pass over to Greg to carry on. Thank you.
Thanks, Sue. Unfortunately, I'm going to start with a definition as well. So the definition of the geotechnical model, the Australian standard gives a great one. So it's the interpretation of ground conditions in a form useful for engineering design or assessment. It may contain a subsurface model detailing geological and engineering characteristics of various materials and groundwater. So obviously, ground conditions, especially over a mine site scale, are often complex and highly variable. And one of the most important tasks for the geotechnical practitioner is to review and simplify these variable ground conditions as much as possible into something useful. So, i.e. a clear and logical framework that can be confidently used for stability analysis and design. The geotechnical model, obviously the ground is in 3D. It presents and communicates the ground conditions. Models can be 3D or 2D. Many of the components of today's geotechnical models are created in 3D, but stability analysis can be either 3D or 2D, depending on the mechanism. And most often the model is illustrated in reports in 2D cross-sections and plans. The closure geotechnical model should include information on the landform design. So that's anything like the pit design, the surface topography, mining, environmental, cultural heritage, or public lease boundaries, and any infrastructure such as buildings, drains, or flood levees. It also includes the geological model. That'll include information on the deposit type, because that's quite important to understand the geotechnical conditions, the stratigraphy, lithology, weathering, alteration, and distribution of geological units. The soil rock mass model, that provides information on engineering properties such as unit weights, intact and rock mass strengths, defect strengths, and things like deformation properties if numeric modelling was to be undertaken. We've also got the structural model. This provides information on the orientation, location, and character of geological defects such as faulting, folding, bedding, jointing, or any fabric. And the groundwater model, the hydrogeology model. So that will cover information on groundwater surfaces, permeability of the rock mass, pore pressures, and pore pressure responses to things like rainfall events. There's also other factors which could be important. So the climate is one. So a mine site located in the tropics, for example, will perform differently from a geotechnical perspective to a mine site located in the arid desert. So just due to the amount of rainfall. A high rainfall environment is going to advance your rates of weathering, erosion, and result in a lot more pore pressure loading events on the slope, which can have an adverse impact on stability. The level of detail in a model typically increases throughout the project cycle. Obviously, a model developed during the planning stages of a project, which is likely to only be based off a small number of boreholes, is going to have a much lower confidence or higher uncertainty than a model based on excavated slopes for an operating mine that's approaching the closure stage. The level of detail that's required in each of those components really depends on its influence on stability. Within a soil or highly weathered rock mass deposit, the material strength governs the stabilities, and pore pressures also play an important role. Within certain types of deposits, such as residual soils, like saprolites, the relic structure of the parent rock mass can also influence stability, so that also needs to be considered. Within soft rock, which typically includes Queensland coal mines, all aspects are important, but intact and rock mass strength and structure are typically the most critical, and pore pressures do play an important role in certain situations such as footwalls or where the stability of the wall is already marginal. Within certain mines, there's some geotechnical features which deserve particular attention. So within coal mines, bedding orientation, bedding strengths, whether it's sheared or not, and the presence of any weak layers such as tufaceous units are very important to identify, as they quite often have a big influence on the stability. Within hard rock, stability is entirely controlled by structure. Where the structural stability is marginal, pore pressures, and in particular transient pore pressures, play a big role on influencing the stability. So during high and prolonged rainfall events, the transient pore pressures can load those structures which may be marginal and cause movement and deformation in the slope. Within variable deposits, so these are things like copper porphyry deposits, all aspects are critical. The key is to understand what controls stability in each rock mass domain and how each rock mass domain interacts and influences the stability of other domains within the same area of the pit. The model for closure is similar to an operational design, but it needs the additional focus on the long-term effects on material properties and performance. So things like weathering, degradation, durability, and erosion over time. This slope here provides a good case study of why that is important. This slope here was excavated within tertiary sediments, so lignites, clays, some reworked basalts, which have since weathered into clays. And these were all capped by an overlying cap of fresh basalt, which continuously recharges groundwater into the underlying clay units. The slope was excavated within a strip mine, so pit walls were sort of turned over every 9 months. The material was relatively stable for those short time frames required for a strip mine. But then mining unexpectedly stopped in the strip, and as the material was prone to desiccation and strain softening over longer time periods, the slope began to deteriorate and experiencing progressive failure. So this is 18 months after the slope was first excavated, and more recently 6 years after, and you can see the effects of this progressive failure on the slope here. So this serves as a good example of why closure models need to include potential long-term effects on material properties and the failure mechanisms. We're going to go through a couple of case studies now to illustrate geotechnical models and how the different important components are presented. We've got one case study of hard rock, which I'll go through, and then Sue's going to go through a coal example. So for this example, this is pretty simple geological conditions. It's an intrusive deposit with shear-hosted mineralization, has various types of granite lithologies with pretty gradational contact boundaries between each, but they're all very similar from strength and durability perspective. So the geology model doesn't actually have a huge impact on stability. For the rock mass model, there are some localized brecciated zones around faulting, but typically it's all high strength, it's all blocky rock mass, and it's not a critical control of inter-ramp or overall scale stability. It does control the bench scale to a certain degree. The hydrogeological model, the VWPs installed in the slope show a depressurized slope. So as mine progresses, the slope quickly depressurizes. But this mine is within the tropics. So transient pore pressures from the wet season, from those high prolonged duration and high rainfall events do have an impact on stability wherever the structural stability may be marginal. But not surprisingly, as you can tell from this image, the stability is entirely controlled by structure. So that's where we've focused our efforts to try and get that part of the geotechnical model as accurate as possible. to do that, we did pretty extensive photogrammetry and field mapping. So this on the left is all the faults that have been mapped using photogrammetry techniques, and on the right, all the joints. We also reviewed a lot of acoustic televiewer boreholes beyond the pit slope to try and get a better understanding of the conditions beyond the pit walls. For any geotechs and geologists there, you'll see there's quite a bit of scatter within all these boreholes. So this is a very complex, structurally complex system. We then used all that data to create a detailed structural model covering the key influences on stability, such as we created 3D surfaces of any major faulting that were inter-ramp scale or greater. We also come up with structural domains. So these are areas of similar structural conditions, which really help to, I guess, remove the scatter from a particular area and make sure you're only making the assessment based on the data that's actually within that spatial area. And we also did a lot of work looking at defect strengths. So separated by defect type, then infill, and we were able to do that from the field mapping exercises and drilling and laboratory testing. So this model then allowed us to identify and quantify the credible failure mechanisms for each area of the pit, which I'll go over a little later in the presentation.
Okay, I'm here to reassure everyone that we don't always have to have it quite that complex. This is an example from the other spectrum. Coal low wall. The void was about 100 metres deep, had a relatively steep floor dip, steep coal seams. 2 strips were mined out by truck and shovel, and as is typical in strip mines, some of the spoil was dumped back into the pit against the box cut. A creek overflowed into the pit while they were still mining, caused large slips in the low wall, and that was when mining had to stop. In the 10 years since, there's been a bit of continuing movement at the cracks, but no further large slips. So in this case, strip mine 2D analysis is fine. You can see that it's a very simple stratigraphy, not much structure, which is typical of spoil. The key driver to stability in this case is the strength change when that spoil becomes saturated. So for the long-term stability assessment, we have to look at as the pit lake is now and the predicted long-term pit lake level and carry the analysis out on that. Another example, this was a high wall, coal high wall for a PRCP final void. I haven't got a photo of the wall because it won't be mined for another decades. So it's really a planning stage, remembering that the PRCP planning part is to demonstrate that you can achieve the requirements of rehabilitation. So the geological model was used to develop the profile, the different layers. Hydrogeological modelling from the PRC and the void water balance modelling gave us the boundary conditions for pore pressures that were analysed between the two. And being central Queensland, there's a fairly good mass of published strength properties for your tertiary, weathered Permian, fresh Permian, those aspects. Simple model, but for the long-term planning at this stage, perfectly adequate. Hopefully we've hammered this enough that the model, we cannot be certain. There's a high level of uncertainty in developing the model. So instead of trying to ignore it or spend an unreasonable amount of effort minimising it, the approach is to address it and admit it. And this is probably one of the key things in both the ACARP and the practice note, is that we've developed an uncertainty rating sheet for the geotechnical model. There are 8 model elements identified, and there's a score assigned to each that reflects their relative importance. And there are different scores for the hard rock and soft rock examples. 4 uncertainty levels for each of those, ranging from what is nicely called introductory to a low uncertainty, which would be when you've done a lot of work testing and probably have the wall there with observation. Description for each combination of model element and level, and simply you sum the score for the element times the weighting for the level, add all of those together for the different elements to get an uncertainty ranking. I won't go through this whole one, but as an example, the top line is geological model. It's a hard rock example, so that's got a score of 10 out of the 100. It was rated as medium uncertainty, so the contribution of that one is 10 times 0.6. The example, the last component, which is, I think, observation and monitoring, it's given quite a lot of weight, and we'll pursue that again later, 25. And in this case, it's been there, there's been quite extensive monitoring, so the score for that one's 25. Add them all up, gave a total of 67, which then comes into medium uncertainty. Now, I want to stress that high uncertainty or medium are not in themselves bad things if it's appropriate to the stage that you're at. What you do is take account of that level of uncertainty in selecting the design acceptance criterion, which we'll get onto a bit later.
And yeah, I just want to highlight, so this was the hard rock example, and you might notice there's two uncertainty weightings given to the structural model. So one of them had a medium uncertainty. We were sort of within 100 meters of the pit walls, because we could actually map the structures in the pit walls, project them with some confidence. But then we had a high uncertainty anywhere where it was sort of 100 meters or so away from exposures, just because of the scatter and the borehole data, the limitations on being able to know what sort of persistence and termination relationships those structures had. So different areas of the pit can have different model uncertainties.
Okay, so thank you everyone for starting to put some questions through. That was a really important session, I think, Greg and Sue, because firstly, it was important for us that this work could be broadened out to discuss hard rock mines and the differences for an assessment that are relevant there. And then also that the model uncertainty statement, I think, is really invaluable to this process and to helping us understand the approach, and that's been great, so thank you for that. We have a question here about closure model best practice. Should parameters around weathering, degradation, etc. be site-based and lab tested, or regional database, or are regional database inputs sufficient? Not so sure who wants to, will I throw that question to someone in particular, or do we draw straws?
I'll start.
Thanks, Sue.
I'll start. One of the problems, well, courses for courses, it depends on how important things are in the model and in the anticipated mechanisms. Weathering in particular always looks worse than it is, or most of the time looks worse than it is. It tends to be a very shallow effect. And so, except for particular cases where you have persistent weak layers, it doesn't penetrate very far. I remember reading one of the highest rate of soil development measured is about 8 mil a year. So what we get on the surface is a degradation and a raveling, which is an aspect of weathering, but it's only physical. But it tends to look worse than it really is. The times that it will matter will be particularly with your residual clays, where long-term properties are different. And I would think in most cases, and particularly for planning, judgment-based use of parameters is fine, but there will always be a few cases where it becomes so absolutely critical that it warrants testing. And this, taking a little time here, but it's part of the value that we haven't stressed here in that uncertainty model for the geotech engineer, is that if it shows up something that we really are uncertain about, but it's important, it gives us some leverage to go back to the client and say, hey, we need to invest some more money in getting this bit better understood, because if we do, we can improve our uncertainty rating and justify a different design acceptance criterion. So I would say most of the time, general assessment, certainly in the COL, but it's always got to be confirmed that that is a situation, because there's a small proportion of cases where it really could matter.
Greg, did you have anything you wanted to add?
No, I think Sue answered that pretty well. But yeah, I mean, it's case by case, really. You know, the hard rock example, that granite's not going to weather very quickly. We can see a lot of, you know, exposures just in natural landscapes where we know that doesn't happen. So, you know, just I guess some justification of why using regional analogues would be fine. But yeah, you know, areas like the tertiary sediment example that I had, like, you know, it's desiccation of the material is obviously a big factor. So yeah, it's really just case by case, and whether weathering could control it does probably need that localized sort of testing.
Okay, that's great. Thank you for the question. I think we might continue on because there's lots more to cover. So thanks.
Okay, I'm up. So credible failure mechanisms. These must be identified and justified for each landform element or zone. So that's your crest, your slope, and your toe. And I've just provided some illustrations here of typical mechanisms such as toppling, wedge planar, wedge player with NUM daylighting, and circular and rotational. The practitioner will use a geotechnical model and engineering judgment to assess the credible failure mechanism. So they need to be appropriately qualified to be able to do so. Importantly, there's quite often multiple potential mechanisms within the same pit slope. So you might have the upper few benches, for example, excavated in deep soil or highly weathered rock. That's going to be controlled by more of a circular style mechanism. Whereas globally, that slope might actually be controlled by a larger structural failure style mechanism within the fresh rock mass below. And both of those mechanisms have the potential to fail beyond the crest, and therefore they both need to be quantified. The mechanisms identified will determine the method of analysis undertaken. And again, that's up to the practitioner's judgment to decide what method of analysis is appropriate. And the assessment of the failure mechanisms needs to account for these changing conditions over time. So like we were saying just before, the weathering, erosion, changes in groundwater is an important one for closure, because you've got to not only assess the groundwater conditions when, you know, the day mining finishes, but also the final pit lake level and, you know, potentially any stages in between. And for NUMAs, small-scale instabilities may be acceptable if the consequence of failure can be proved to be negligible or low. The consequence assessment, this aims to identify the likely harm if instability was to occur based on the identified critical failure mechanisms. This table's been taken from the ACUP study report and can be used to help guide the assessment. The assessment ranks the potential consequence of failure from negligible to high consequence against 3 harm categories. So harm to humans, environmental harm, and property loss and damage. And the table provides some qualifiers to help guide the practitioner's selection for each. Obviously, the higher the consequence of failure, typically the higher the design acceptance criteria value should be for that failure mechanism. This is an example from our hard rock case study of the consequence assessment that we did. So what we did for each area of the pit, we defined the extent of instability and the exposure within the extent based on the credible failure mechanisms and infrastructure across that final landform. We did this for the crest zone, the body of slope, and the toe of the slope. We then assigned a consequence category through here for each mechanism against each element of harm and provided commentary in the table justifying that selection. We also provided a map illustrating the different maximum consequence areas across the pit. This was often defined by what infrastructure was within the plausible instability zone beyond the crest. You can see this red polygon here. That's an area of heritage listed significance, so obviously a high consequence for property loss and damage, which we've got circled in this red box up here. This orange zone, some of you may notice there is an out of pit waste dump quite close to the crest. That orange zone is covered in its own separate assessment table. And that's been assessed to have a moderate consequence of environmental harm, just due to the fact that if the slope failure was to occur in there, extending into the waste dump, the failure would mean there's some moderate rehabilitation, remediation earthworks required if the failure was to extend in there, just to be able to remediate that failure. The rest of the pit didn't really have any infrastructure or anything near the crest, and access was going to be excluded on enclosure, and therefore the consequence of failure was assigned negligible or low for those areas. The design acceptance criteria, that defines a threshold for acceptable stability. So if a landform achieves the design acceptance criteria selected, then it can be considered geotechnically stable. There's a lot of different methods of stability analysis, and each of these different methods can produce a different parameter value for the design acceptance criteria. For example, a factor of safety. The factor of safety is the ratio of available shear strength of the soil or rock mass to the shear stress required to cause failure along the potential slip surface. A strength reduction factor, or SRF, that's a factor by which the shear strength parameters are progressively reduced until non-convergence occurs within a numerical model, i.e. failure. And SRF and factor of safety are typically taken to be the same. A kinematic probability of failure, POF, these are used for structurally controlled designs and is the likelihood expressed as a percentage or probability that defects will intersect to produce an unstable volume of rock mass for any given slope orientation. There may also be other design acceptance criteria more appropriate for the situation. An example could be acceptable deformation limits, where minor movement may be tolerable, so all slopes do move. Some mechanisms, such as toppling mechanisms, can move a long way before the slope progresses to collapse. I've personally been involved in managing a slope which moved more than 10 meters and didn't end up progressing through to collapse. So deformation limits may be an alternative design acceptance criteria if small but manageable movement is anticipated. Again, the appropriate value for the design acceptance criteria is basically up to the practitioner to use their judgment with justification provided. And the appropriate value will be selected based on the model uncertainty and consequence category. So higher uncertainty, higher consequence should mean a higher design acceptance criteria. So some suggested ranges for design acceptance criteria are appended to the practice note and also in published literature such as the large open pit guidelines for mine closure. And the practitioner should be aware of typical industry acceptance criteria for different methods of analysis and risk profiles. Stability may be quantified using observational or analytical methods. Observational methods, they don't quantify stability directly, but they do quantify the slope performance over time. So for example, if a slope has been standing stable for 30 years with little signs of degradation or instability, there's a good chance it will stand for another 30 years, so long as the loading conditions do not change. Sue's going to provide an example of the observational assessment in her case study shortly. As far as analytical methods, they can include empirical methods. So these are experience-based correlations, benchmarking, such as stability design charts, for For example, these may show stable and failed case study slopes over different angles and heights within the same geotechnical conditions. Deterministic, so these include limit equilibrium, which is very commonly used. Limit equilibrium provides a factor of safety. It's typically applied to interramp and overall slopes where stability is controlled by soil and rock mass strength, with or without some structural anisotropy. Numerical analysis, so that provides a strength reduction factor. That analysis can allow for the impacts of stress redistribution within a slope as it moves. Good for quantifying progressive failure mechanisms and quantify deformation levels. And probabilistic methods for evaluating stability. So these provide a probability of failure and allows for incorporating variability and uncertainty in the parameters. These may be more useful, for example, with structurally controlled slope in the planning phase, where you might only have a data set of structural orientations from boreholes with a limited understanding of the spatial location and persistence of the defects. And you've got to design the slope using a statistical method to ensure only a small percentage of those defects are kinematically unstable, which then becomes your probability of failure. And typically, the level of analytical sophistication will increase as the projects advance and the geotechnical model uncertainty decreases. So you wouldn't expect to see advanced numerical modeling within a project that's in the sort of scoping or pre-feasibility stage, because the model uncertainty is going to be so high that it's going to have a major impact on the reliability of the analysis. So I'm going to go through a case study from our hard rock case study now. So for that, we used multiple analysis methods due to the complex conditions. We made good use of the fact that this mine had been in operation for 40 odd years, and they'd mined a series of cutbacks within the same rock mass at steeper slope angles that were actually planned for actually being proposed for this final design. So you can see here, they've successfully mined interramp angles up to 64 degrees. The rockfall risk within that, you can probably see there's not many berms or anything like that. So that is something to take into account, but on the overall scale, it did manage to stand up. To quantify this, we first measured the interramp to overall slope performance by assessing achieved probability of failure of the current and historic slopes. So we measured any areas of the pit that had failed on a multiple bench or greater scale, and measured that as a percentage of the total pit wall area. That confirmed that even when mining steeper pit wall angles had been used in the past, the interramp to overall slope performance was within acceptable design acceptance bounds for mine closure, so the probability of failure overall was less than 5%. So that gave some confidence that the proposed design angles were achievable within acceptable probability of failure limits, so long as the structural conditions were consistent. So we still needed to do some further analysis to quantify the conditions and make sure that there was no kinematically unstable intersections within these proposed final walls. So we did that, first of all, by just looking at all the modelled 3D structures that we did a basic discrete kinematic check, essentially on the major structure intersections, using all our mapped and modelled structures with respect to the pit wall aspect and location of the pit wall that they intersect. So that really helped to present and understand the failure mechanisms that we were dealing with. So the scale, whether they were a wedge or more of a complex mechanism. And that sort of helped feed into the more advanced analysis that we also did. This is one example of the advanced analysis that we did. So we did a deterministic 3D limit equilibrium analysis on the mapped and modelled faults. That checks for the potential kinematically unstable wedge and complex 3D mechanisms. The good thing about this particular type of analysis is that it also checks for successive block failure, i.e. a progressive failure. So within hard rock mines, often the loss of a key block in the slope or a failure of a small wedge in the middle of the slope can destabilize wedges further up the slope. So i.e. triggers a progressive mechanism much larger than that original wedge failure. So the result of that analysis was we identified areas where there was larger failure mechanisms, and in any areas where there was a high consequence of failure, we modified the design to remove those larger failures from impacting the crest and keep the overall design within acceptable probability of failure limits. So as you can see, this area here is actually that area of the pit there. So as you can see, there's still smaller, bench scale instabilities, but because it's a NUMA, they're not impacting the crest. They've been assessed as being acceptable, and none of the wedges are anticipated to impact beyond the crests there. So that was a good outcome. Now I'll throw it back to Sue.
Back to the easy stuff, the coal mines. There's a reason I stick to the coal mines, I can tell you. Again, this one, it's a typical coal mine void in a strip mine. In this case, the high wall and low wall on the same. The model reliability was considered high uncertainty. The consequence of instability within the NUMA, however, was negligible. As I said, 2D analysis. Considering the uncertainty and consequence, a design acceptance criterion of safety of 1.25 was selected for the NUMA, and these show the results of the minimum factor of safety for both high wall and low wall, and for both the end of mine when the pit was dry and the long-term pit lake level. And just quickly there, one of the things that a geotech is that you didn't get something unexpected in the analysis. And in this case, the minimum factor of safety slip surfaces all connected with a layer you can see under the floor, which is the Yarrabee tuff, which is what we all know and hate. And so that's reassuring on it. Now, this was for the NUMA, and there's a bit of an awkwardness in that the Rehab Commissioner's remit on this was specifically the NUMAs, but normally when you do a void stability, you've also got to consider the impact, not just within the NUMA, interact with adjoining PMLUs. So in this case, the stability was still pretty good, but for example, a grazing PMLU, you might consider that the appropriate factor of safety there was 1.5 rather than 1.25. But the important thing is that is only assessed at the boundary of that post-mining land use, at the grazing limit. And your options are either, if it's not so, you set back the boundary of that to where you achieve it, if you can, or you can stabilise. So you've got two different alternatives. If you don't meet your design acceptance criteria, either change the consequences by changing where your more valuable features are, if you can, for example, a road or a grazing boundary. Or if you can't do that, if it's a river, then you have to look at alternative measures to either stabilise, or again, you may have opportunity further investigation to improve your certainty in your model. This observation determination, it isn't respected, I think, as much as it should be. We do a lot, it's very normal in operations during mining to assess stability by a documented inspection. Once you've got your basic geotech model and you understand the mechanisms that could give you problem, just observing whether or not they are manifesting is the strongest indication of stability you can have. Also, if you're observing an existing wall, you've already taken away all the uncertainty between at your desk and designing in that point. If it's stable today, then it's only likely to become unstable in the future if there is a change either to the ground stresses or strengths. So going forward for long term simplifies down to identifying potential changes. any given observation is a point in time, granted, but if you've got all your operational inspections and then going through the period while rehab is being undertaken, you can build up a time, and that does give you some good insight into the nature and rate of any of the changes that may occur. So to use observation as a method to evaluate long-term stability, you start off by identifying from your geotechnical model what are the credible potential future stress and strength changes, be it relaxation, changes in moisture content, those sort of things. Then give consideration to the likelihood, rate and impacts of those changes, and your time series observation is very helpful in that. And having made the assessment, of course, you continue to evaluate and check that everything's going as expected by observation. To be useful, the main thing to do is to capture repeated inspections or observations in a consistent form so that you can compare this trend over time. So a inspection performer is the obvious way to do it. The standard information about the date, location, your existing geometry that you're looking at, and then importantly, observation of any stability related features. For example, is there evidence of tension cracking, rock falls, whether they're small or large, seepage at the face. Also, this is where you can better assess the extent of erosion and weathering, and if they are occurring in any way that could trigger those ground stress changes that would lead to instability. So this example is a coal mine high wall. Photo was taken when it was 17 years old. It's now 25 years old, and really there's blood oil change. The geotech model was quite shallow tertiary and weathered zones. You can see that the grey, the unweathered, extends quite a way up. There were two sets of adversely oriented defects. They were at quite close, tense spacing, and that's actually a good thing because that means you tend, if they intersect unfavourably, you'll get small pieces of rock rather than large wedges coming out. The high wall had a pretty small catchment of runoff draining over it. The condition to date, you can see there, localised moderate erosion, but it's all going down the face, not causing any undercutting. There's no slumping or existing geotech failures. There's evidence of small localised rockfall, fist-sized fragments falling off, and a little bit of crest retreat, but no big gouges. So in that, the anticipated future load changes is that the ongoing stress relief could open those defects, those joints a little bit more. You can expect some continuing small rock falls or ravelling, as we call it. And of course, in the long term, lake level, it's quite low at present. And given that the base of weathering is a long way up the wall, it's unlikely in the prediction water table wasn't going to get up there where the materials are susceptible to strength change on wetting, no undercutting. So on the basis of all of that, the determination by observation is that the geotech stability will be adequate for a NUMA, continue that way for at least 50 years. If it's been stable for 25 and there's no evidence of developing beyond that little surface ravelling, it's reasonable to forecast that twice the existing time frame it will continue in that way.
Okay.
Short breath.
Yes, everyone take a breath. We've got a couple of questions. Well, we've got lots of questions, but time for a couple. A question from Kane. How to account for slaking of saturated materials in coal mine voids, and do you get a loss of strength over time that needs to be accounted for? I'm assuming, Sue, you might like to take that one.
Okay, I can start on it. Again, slaking is part of this degradation aspect, and it really is a fairly shallow phenomenon. You certainly are aware of it already operationally. It tends by and large to cause a bit of surface ravelling, so you certainly wouldn't promote a particular void for water sport where someone was getting close to the hole. In a NUMA, unless there's a particular, and I can think of a couple, but unless it's a case where a tending to slake material is underneath a harder material and you can get the undercutting, it doesn't usually cause much trouble, a little bit of retreat. So it's more an identifying, if you've got, it's really slaking, as I say, it's one of those ones that looks bad, but it usually only goes back, the wetting front only moves so far. And so it's quite a slow thing. If you have those sort of circumstances where you're undercutting another layer and you can then create a toppling type failure or a major wedge, they're the only cases where it's a biggie. There's a lot of ways of assessing slaking for the purpose of operational. They're all quite simplified because we want them quickly. It's, I suppose I didn't mention with weather, and one of the hardest things is how do you test something now for its condition in 50 years' time? So it's more building on this existing, but we've got high walls in the basin that have been there 50 years now. Now they aren't always representative of all of them, but we've really got to use the field tests that we've got to draw those assessments.
Thank you. A question for Greg. How do you take the influence of mining activity to the rock stability into consideration? The hard rock model seems to be based on initial geotechnical investigations instead of post-mining investigation.
So the hard rock model, that mine is in operation. So a lot of the data is being, I guess it is a progressive rehab, like a really, it's a quintessential progressive rehab closure plan. The data, the model confidence is such that we basically need to continue mapping, continue collecting data all the way through mining for this one. Because as you saw in those initial investigations, there's a lot of scatter, so we can't really reliably predict exactly what the final hole conditions are going to be. We do control, so as far as mining related disturbances, we do try and control the blasting as much as possible to reduce the impacts of blast effects. We monitor the pit walls using prisms and radars, so any areas that look like, you know, they're showing any subtle movements, we'll have a more detailed look at those and what the potential impacts on the final closure void are going to be, because it's a long mine life. There's going to be opportunities if there are any areas where the conditions were slightly different and maybe lower factor of safety than first predicted. We do have the ability to potentially backfill, step the design out, that sort of thing, but we are monitoring the slope very closely to be able to do that before it gets to the point where I guess it starts failing. Yeah.
Okay, thank you. I think we might continue moving on because time is starting to catch up with us and we have a little bit more to hear about. So we'll continue. Thank you.
We are on the homeward run. This component, this element of the assessment, a safety assessment, those who are familiar with safety, ALARP, as low as reasonably practicable, implies that even if your evaluation says that your slope has met the design acceptance criterion, if there are additional measures you can apply with reasonable ease and costs that reduce your risk still further, then good practice is to apply them. So to do this part of the assessment, you basically use the same hazards you identified in the consequence category assessment, in the added context that you now have the outcomes of the stability evaluation, but it's still about okay, what are the foreseeable changes going forward? This assessment is typically qualitative. The aim isn't to quantify the remaining risk, but to identify any measures that can reduce it a bit more regardless of what it is. And the typical measures that come out would be access exclusion, particularly for NUMAs, you know, your bund, your fencing signs, and there's potential to document any constraints in a land management plan that would be attached to the land tenure, the title at close of mining. In the practice note, we have deliberately not provided a method and left that for the Geotech AQP's discretion. The main thing we wanted to get in here at present is that that assessment is done. So you don't just finish the assessment with it's met the design acceptance criteria with. So that extra, given that we know it's long term, are there a few extra things that we can add? Greg? Last component is the certification, which really is formalising what is already our professional responsibility. Stability assessment is considered a professional engineering service, and therefore it is governed by the Professional Engineers Act. That requires that the work be undertaken or directly supervised by a competent geotechnical RPEQ. It requires that our communications and our evaluations in the assessment report are specific and accurate. And this is important because it comes down that given the uncertainties going into the future, if we were to write that we guarantee stability indefinitely, that could be taken as a breach of the Act because that's stating something that we can't be sure of. And that's where this whole process of focusing on the reliable and repeatable process came from. As I say, we're already bound by those standards under the Professional Engineers Act. Certification is a way to just provide clarity and confidence to the reader, be it the client or the regulator. So you state clearly that accepted practice was followed, although as an RPEQ, I can't imagine you what you would have been doing following non-accepted practice. You get a chance to restate the outcome of the assessment away from all the words and geeky stuff put in the middle of the report, and reiterate your limitations and assumptions, which may just be by reference back to the statement of design. We put in a quick bit on monitoring after closure, just for some guidance. Obviously, particularly when you've been designing, nothing beats the proof in the pudding of observing it at the end. It validates your assumptions, confirms your performance, one hopes, or gives you an opportunity to modify if necessary. The typical ways of monitoring are obviously visual inspection, movement measurement sometimes, and groundwater levels. But which of those measures are justified or required, and the frequency should be at the judgment of the AQP. One would expect them, however, to reduce over time and to largely cease before lease surrender. So, takeaways that we wanted to convey today is that long-term geotechnical stability can't be certified. However, we can certify that we have followed a reasonable process in the evaluation. And that process needs to be risk-based, but also depends heavily on the judgment of the Geotech AQP. Next point is that the design acceptance criteria has to be based on consideration of uncertainty and consequence, and I suppose the identified instability mechanisms. The upshot of that is that factor of safety is not always the appropriate measure, and even if it is, there's no magic about 1.5. That may not be the appropriate value. Observation analysis and risk controls must all contribute to managing NUMA voids, and the assessment report to be able to provide the confidence that the regulator requires, it has to be transparent, defensible, and reviewable by an independent peer. And I think that just about gets us to the end.
It sure does. Thank you. So we have some questions, which I'll start to roll through so we can use our last 15, 20 minutes wisely. So a question from Darren. Thanks, Sue. In the world driven by processes that lead to penniplation, that is the process by which a relatively flat land surface is produced through a long period of erosion, what is a realistic time frame for applying geotechnical safety assessments post-closure? And that sort of circles back to one of your earlier slides that we had.
Geotechnical stability is, it really will be somewhere, depending on your particular model, your mechanisms, your data, something in the range of half a century to 2 centuries is about the limit. We just don't have verified information any further. We have indication of geomorphology, but we certainly can't quantify any further than that. I came across this when, in the early days, working with a geologist or geologists on some of these stability assessments, and they shrug their shoulders and say, it's all going to fail. Well, yes, in geologic time, but we're really not 1,000 years. So it's really, and that's part of this process, is being honest and upfront and saying, this is the time frame over which we believe it's reasonable, and that we have confidence in our evaluation. And that's it. It's at best a couple of 100 years, depending on the material, quite often less than.
Thank you. And that's a question that a lot of people have, isn't it? So it's good for us to be able to discuss that. We have another question here, and maybe Greg, you might be able to answer, I'm not sure. What factors should be considered when determining locations for piezo installation and to monitor the geotechnical stability parameters? So what should we think about when we're thinking about where to put our piezo's?
So I guess the short answer would be anywhere where the pore pressures are playing a pretty large role in the stability. So you may have an example where you've got a hard rock and you're worried about a certain wedge configuration or something like that, and where you don't want any high pore pressures acting on that wedge. Therefore, you would look to install piezometers either side of the fault, behind the fault, so to make sure that we're not getting high pore pressures behind that wedge and essentially sort of pushing it out. Other examples, maybe there's been mine sites where I've been involved at where in order to achieve an acceptable factor of safety, you need to achieve a certain amount of depressurization. So if you've got hydrostatic conditions, the factor of safety may be close to 1. If you've got much more reduced pore pressures, the factor of safety is 1.5. It can be that extreme. So you'd obviously need a lot of piezometers in a rock mass or soil mass like that to prove that you've achieved the pore pressures which are required to meet that design acceptance criteria. So yeah, quite often they are targeting certain stability situations. If there is nothing really to worry about, it might just be a sort of general monitoring of making sure that the pore pressures aren't astronomical in the general rock mass. But yeah, they're normally targeted towards a certain requirement.
Thank you. A question here about 2D versus 3D modelling. While 2D modelling is faster for specific details, 3D offers comprehensive visualization. My question is how to determine whether a 2D or 3D approach should be used for a specific project based on your professional experience. Thank you. I'll open the floor.
I'll start with the easy. I'll start with the easy stuff. In the first case, it's about identifying your stability mechanism and can it be well enough approximated by 2D? So coal strip mines are often that, except you hit particular features like faults in it. 3D is where the mechanism's 3D, then you've got to go for it. But we do have a problem, particularly with limit equilibrium analysis. Even though it's a 3D situation, we do not have the body of experience to give us confidence in assessing the appropriate design acceptance criteria. So quite often, I think if you honestly believe 3D was your best, you'd put it there, but you may also do a 2D, because we have a lot of experience of knowing that if we this factor of safety in a 2D, then we're probably going to be okay anyway. So we're still in the process with the 3D of building the body of knowledge that gives us confidence about what the appropriate factors of safety are. There is some guidance in the appendices to the note, but it's quite awkward there. It's also a case that one can't really do 3D analysis until one's got a quite detailed understanding of the profile. And Greg may be able to talk more about that just briefly.
Yeah, so take our hard rock case study. The 2D analysis, we did it based on anything that's any faults which struck fairly parallel with the wall, but it didn't really give us a realistic idea of the actual stability, because all the instability mechanisms really were more 3D. So they were more wedge, they're more like complex wedge mechanisms. So they have to be analysed in 3D for those certain situations. The other type of situation might be where the pit topography has a big impact on the stability. So in the case study that I provided in the practice note as an example, so that was a mine which had been already excavated in care and maintenance. There was a diversion drain back from the crest, and we did 2D LE to start with in the end wall, but it was a really sort of, I guess, narrow circular pit. And the 2D analysis was really quite conservative because it didn't take into account any of the effects, the positive effects on stability of that 3D buttressing of the pit wall. So we also did 3D limit equilibrium as well as that. So yeah, 3D really is required wherever it's a 3D problem with the pit wall topography, or it's a really 3D problem with your failure mechanism.
Thank you both. That was good. We have a question now that's a little bit longer. It's like a two-pronged version. So, how is the effectiveness of changes made to the model assessed when a model shows medium or high uncertainty? So I'll read that again. How is the effectiveness of changes made to the model assessed when a model shows medium or high uncertainty? Additionally, what is the accepted level of residual risk for the NUMAs? Is there always going to be a degree of uncertainty, and is this determined through a standard framework or on a case-by-case basis? Which sort of brings us to the point of this work in some ways, doesn't it? I'll just throw that across to you both.
Okay.
So I'll have a go first, Sue. So the effectiveness of changes made to the model assessed. So the table does give some guidance, some qualifiers of where you might be able to sort of move it from a medium uncertainty to low uncertainty, and that might be more localized sort of testing, further investigation. So if there is something that if you look at your failure mechanism, and for example, in a coal mine, it really depends on the bedding strength. So whether the bedding strength is sheared or non-sheared has a big impact on your factor of safety and final design acceptance criteria. So you may do targeted investigations to quantify whether that bedding shearing is present or not, and that will then help you move down to a low uncertainty in your model certainty criteria. What was the second part? What is the accepted level of residual risk for these NUMAs? So the residual risk, I guess, comes into the design acceptance criteria. If there's a lot of uncertainty and the risks are high, then you're going to have to take that higher design acceptance criteria, which allows for that, I guess, the sort of, I guess, all the uncertainty within your models. if there's going to be a degree of uncertainty determined by a standard framework or case-by-case basis. And yeah, I think everything, the thing I've learned about these closure studies is it's almost always case-by-case basis. I've been involved in probably about 10 different PRCP closure projects, and the acceptance criteria and the method of analysis and everything that we use is almost slightly different in each, because it's all got different rock types, different failure consequences, different mechanisms, and different, I guess, residual risk from a potential instability. Hopefully that's answered some of it. Okay, so
I'll slip a little bit in about the residual risk, which is there's an existing version, it's under redevelopment again, but the residual risk framework for the government is the basically identifying not the cost of necessary rectification if the identified hazard occurs, by context of the probability. So if you were, I can't, in NUMA where there's not much around it, just some grazing and woodland, I can't see, I would be surprised if the residual risk quotient, which is a mechanism, repair times likelihood, would trigger the quotient and go to a payment. The sort of place, it's very much different in tailing dams and things. But if you had a high value feature near the void, for example, a major public road or a watercourse, that's where the residual risk takes account of that even though it's an acceptably low probability, you still have to make allowance for it there. So there's a bit of scope for playing the lower the remaining, the more conservative you are in your closure, then the less likely you are to trigger a significant residual risk. But the way the regulation in the PRCP whole framework is now, it's chased down quite a long way. You know, the whole idea of selecting design acceptance criteria in the context of those, for example, if you had the river nearby, has already driven it down quite a long way. And I don't think there's a little bit of scope, but not much, for the mine owner to take on a high, or to impose a high level of residual risk at the end. If you do, it will cost you in the residual risk payment. So quite rightly, the combined mechanisms of the PRCP closure and residual risk are driving a practical minimisation. I mean, you can't get down to zero risk, but it is quite a low level if it passes through all those gates.
Thank you. And that was a really thoughtful question that made everybody think hard as we answered that. So that was good. One final question for the morning. How do climate change considerations play into the assessment?
So we've got a surface water team at PSM, and I know that they do have to consider the impacts of climate change on certain rainfall modelling and flood modelling. So that's probably, I guess, the biggest impact. So that would be, yeah, your flood modelling, your levee design, and then we would need to take that into account to work out if there's going to be any overtopping events of the levee based on climate change scenarios, and then what's the potential erosion effects of overtopping of the levee and that sort of thing. I think based on my experience, that's probably the main impact on these closure assessments.
And I'd point out that if the climate change assessment quite rightly impacts your levee, that's where you put the attention, not the NUMA. So it impacts your levee design rather than where it will catch in a void or a NUMA is where under current assessment, you do not require flood protection, that you might under climate change, and also that it can change your predicted long-term pit lake level. So they're the two aspects. It doesn't, climate change doesn't really, in the scale of and in the time frame of climate change, it doesn't affect the geotechnical properties or model. It changes the water-related loadings that you might have to consider.
Great, thank you. Well, I think we've come to the end. It's been a very fulsome discussion and a busy morning. I do appreciate everyone's help in pulling this presentation together today, and also to the folks who've joined. We'll have come up on the screen soon a feedback survey, so a QR code. I would encourage you please to click on that with your phone, your camera on your phone. It is only a short survey, just a couple of questions, won't take long, but it really does assist us as we continue to develop our workshops. Thank you to Greg and Sue and Sam. It's been very interesting. We have another workshop coming up next week, actually, on a technical paper we published last year on creating alternate growth media if you have a topsoil deficit at site. So if you haven't already registered for one of those events, please do so. But in the meanwhile, thank you everyone for joining us. It's been a pleasure, and we'll see you next time. Thank you.
Thanks, Lisa.